Speaker should be Cristina, but they switch with Raffaella, so Raffaella starts the lecture this morning, and then Cristina is going to give her talk. So let's going to start with Raffaella, her last lecture, and so thank you very much, Raffaella.
Thanks. So yeah, we did this switch. So then you start where we end essentially yesterday with some jets, and then Christina will finish the school with a bang on galactic archaeology. So that's the best way to wrap up this school. So okay, this is the fourth lecture, and as you have seen in the list that is about the impact of jet on the interstellar medium. Again, related to whether they can do anything on galaxy evolution, and if so, what. And so, okay, let's see how far we get with this. So already from the second lesson, I show you this cosmological simulation, and I show you how in this cosmological simulation the energy that the active black hole release is in burst. This is how they implement. And I also mentioned that essentially, if you look in the literature, there are two modes in which negative feedback is provided by the AGN. So there is the so-called quasar mode that is really outflow. So the energy release get rid, helping getting rid of the gas and so stopping star formation. Or there is the so-called jet maintenance. We still have to decide the name, in which the jet, the radio jet, prevents the gas from cooling, particularly hot gas, from cooling and then fueling more star formation. So let's say 10 years ago, we thought, okay, this is it, this is our scenario. We just need to find, we know about it, we just need to find some outflow, measure them, and we are done. And then, of course, it's never so easy, and we are still struggling with this, actually, in the field. Yeah, very much so. So, another thing, one thing before I start that I want to mention, because it's also relevant for this presentation, about the simulation. I keep on showing this cosmological simulation that, yeah, they simulate the entire universe. So, as you can imagine, they have to put some recipe to convert whatever the AGN does in the energy that release. So they always run into problem of resolution, detail, physics that they can include. So there are a number of so-called zoom-in simulation. Instead, looking at specific situation, so extracting one of these objects, for example, and looking at specific situation and including specific and more detailed physics. So these are, of course, very, very important, and you can find plenty in the literature. So the simulation world is divided in this big simulation and the one more detailed. So, and jet, the other thing that I want to mention, jets are very difficult to be included in the cosmological simulation, because you have to put the magnetic field, that is already something very scary, the electron, the way a jet is produced. So, but there are is it running? There are simulation ongoing that they try, zoom-in simulation, that they try to include jets and also to reproduce, this is the X-ray emissivity, the cavity that we have seen multiple times in this lesson. So this is not a cosmological simulation, but extract an object, extract a situation, and tries to include a jet in a certain medium and see whether they can reproduce what we see. So these are simulations, and you will see a few more in the course of this lesson, that are relevant for for the detailed study, because at the end we want to give observational result to the simulator, and they should be included the most. I mean, it's a tough job, but they should do their best to include a more realistic situation. Okay, so the dichotomy that I showed you before, this one, quasar mode and maintenance mode, is very handy if you want to study. You know, you have two boxes, nice. But how realistic is this? And so, is it this maybe the situation that also radio jet can produce outflow, and so give another impact, not only on the large scale, but also on the small scale? And why this is relevant at all, I mean, who cares? But in a way, the more you know, so you need to know how many of the active galactic nuclei can provide impact on your galaxy. If they are only the ones that have a lot of radiation, emission lines, I don't know, high energetic in radiation, that's one, so it's a group of AGN. If also the radio one provides some impact, of course you expand the number of galaxy or a situation in which you can have impact. So for the overall energetic budget, this is important. Okay, so before entering some of the detail, I just of how this works, certainly for the jet. I just wanted to clarify a couple of concepts. So I've been talking about outflow, but energy released by the AGN. But actually, you need some specific situation to be met in order for this energy to do something, because you can release energy, and that goes through your medium without interacting, and so who cares? So there are two parameters that no matter what kind of feedback, what kind of AGN you are looking at, you need to look into. One are the energetics, so do you have enough energy actually to do the job? I've been talking about powerful AGN, low luminosity AGN, so you can imagine a low luminosity AGN may not have the energy, may not release enough energy to do to drive whatever outflow you find. And the other most important is how this energy coupled with the interstellar medium, because if it just goes through, then nothing is happening. So that's something that that people are looking very much into with the observation, well, also with the simulation actually. And then of course your feedback has to start from the nuclear region and has to go into the intergalactic medium, intercluster medium, depends. But this is maybe less relevant for this lesson. So let me just quickly go through what kind of scenario people think of. So if your AGN emits radiation, so is emit radiation that usually you observe in the optical emission lines, this kind of thing. One of the idea is that the radiation is emitted already from the accretion disk. So the accretion disk is very hot, can emit UV radiation. And this UV radiation can produce winds that expand and then shock the surrounding gas. So coupled with the surrounding gas via shocks, because they are fast wind. And then this shock gas produce on larger scale outflow, really material leaving the central region, let's say. So this is one of the scenarios that some of the authors have proposed. In particular, these two authors have been very active. And so you have your quasar, they call quasar, but it's a radiative powerful AGN, and then emits the radiation, and then you have a first region of shocks with the surrounding medium that is dense, and then the expansion of this medium into an outflow. And you can see also two scenarios, energy-driven, momentum-driven, but I'll skip this because it's an entire lesson just on this. So essentially what you measure, how you establish whether your AGN is powerful enough or how much energy it carries is by looking at the bolometric luminosity of your AGN. So really, not the Eddington luminosity, that is the potential energy that your black hole has, but the one that really your AGN emits. So there is an efficiency factor here. And so, if you remember in the second lesson, there was a cartoon on the radiative efficient AGN versus radiative inefficient, and this is exactly what would tell you how much the bolometric luminosity is. Then you can compare this bolometric luminosity, we'll get back to this in a moment, with the outflow, the kinetic energy in your outflow, and see whether they match, whether you have enough energy. In all this scenario, the gas is not smooth, can be in clouds, and the clouds are very important because it's where dense gas is present and can also cool quickly. And as we will see, some of the outflow have molecular gas, so this becomes how the structure of the gas is very important. Okay, so these are the energetic, the bolometric luminosity is really, that is estimated always in some indirect ways, very difficult also to derive this, but it's for, if you think that your outflow is driven by radiation. Then we have the jet, and if you think your outflow is driven by a jet, you need to know the jet power. So you need to know really, as we mentioned a few times already, how much is the energy carried by the jet. Not emitted by the jet, but really carried. And so there are this, we have already mentioned that there are this cavity is one of the ways, probably the most popular way to derive the jet power. It has been done for an handful of objects, I'm afraid, but and so essentially, I just wanted to spend 2 slides on it. Essentially, you see how much power, energy you need to build a cavity like this, to empty this region from the hot gas that instead is around it. You see how much energy you need for that, and then you say, okay, then my jet, that is the only thing I see there, must have this power. So there is an entire literature about this, and people can give many lectures on this. Certainly McNamara, that has really initiated this quite important work. And so essentially what you see here is that they estimated the energy based on the energy that has the cavity has, so the work that something should do to empty, but also the pressure that should maintain whatever create the cavity should also maintain for a long period of time, because it takes quite some time to build this cavity. And so you can estimate the energy in the cavity with some assumption that not everybody is happy with, but I'll spare you the discussion. And then if there are also shocks that you would see maybe in your X-ray emission, you have to take into account also those. So actually what I want to show you is by doing this type of calculation in which you do some assumption, of course, about the volume of the cavity, about how long it took, and you assume that it's the sound speed at which all this travel. That is not true, but okay. If you do all this calculation for the objects that are available so far, as I told you, you are limited to objects where you can see the cavity, so really deep Chandra observation. This is your sample. And what you see here, that is a key plot that many people use, is the luminosity, the power that you think have been necessary to build and to maintain the X-ray cavity. You have on this axis. And then here you have the luminosity, the radioluminosity at one particular frequency. It doesn't matter this, but the radioluminosity that you observe and you measure, your radio observation. And so if you do this and you find this scatter correlation, what you see, and is very interesting, is that the power that you need is actually always between 10 and 100, maybe even more, times more than the luminosity, the radioluminosity that you measure. So this is telling you that your jet carries much more power than just what you measure in your radio image, the same. So, so this is important because this is really the energy that the jet put in, and so it's a key. It's like the bolometric luminosity for the radiation. It's a key number that you want to derive. So I also put one example just to make a bit more concrete. You have this object that you have seen already many times. You will remember forever this object, Drª, where you have the cavity and your radio, that is the red one. And so you can measure in some way from the X-ray the temperature, the density, so you can derive the pressure. You can derive the volume by measuring in some way, with some assumption, the size of your cavity. And so then you have to decide whether there are shocks or not. But in all this way, you can derive, also assuming how long it took to build the cavity, that is another very uncertain number, but okay, how much energy you need. And so if you use this number for Drª will end up in this point in the plot. So it's telling you that in the cavity there is about 10 times, this is the line of 10 times more energy than what you just measured from radiation. This is a plot very much used to derive the energy in the jet. Has some drawback, of course, as we discussed also the other day, that as the jet becomes lower and lower luminosity, the jet are lower, they are turbulence, they can entrain, so the jet is also made by heavy particle. So it's unclear how really we can extrapolate, and you see that it's also a bit scattered. But still, it's one of the few ways we have to know the power of the jet. Okay, but so in principle we have what we need to say something about the energetic. Now I want to show you something that also has quite changed the field of interaction of radio jet with the medium, that is how the jet may couple with the medium. Because until, maybe less than 10 years ago, the jet were completely ignoring in this feedback idea, because the idea was, okay, they are collimated, so they go through the galaxy like a laser beam, who cares? They do no damage, so why should we bother about? That maybe is the point, I don't know, but so if you look on this, in this simulation, similar to what I showed you yesterday, these were simulations made of a jet expanding in a uniform medium. And this is what was used until, this is, you see some of the paper, maybe even older, because they are already consuming enough, time consuming enough. But so this, you see the jet entering with this partly disturbed, but stays very collimated. So the part that is affected is essentially this one. So this is what was always done, until a more realistic simulation were introduced, and are the one that actually, this group started, and are simulation of jet entering a clumpy medium that, as you can imagine, I mean, you work on the galaxy, and this is a much more realistic situation. So if you launch a jet in a clumpy medium, the jet will start interacting with all these clouds around it. And this interaction will create, well, first of all, will spread, the plasma will create this larger cocoon and shock around it. So what is happening is that the influence of the jet gets transmitted via this interaction with the cloud in a much larger area and volume. So also, if you look at the time, this is how long it took for this jet to get about 1 kiloparsec. This is the box here, while this is still trying to get there, just because of all this interaction with the cloud around it. So the energy keep on being dumped in the medium around. So it's quite a completely, quite a different situation, as you can see. So the starting of this more realistic simulation have also triggered more interest on, okay, now let's look at really the impact of the jet. I have more of this simulation, so if you have missed the first one, then you will get all the other. So, so this is essentially the same as another. You can change many parameters. This is a powerful radio jet, but what I wanted to highlight here is okay. First of all, you have the clump, you have the clouds, and this cloud gets partly or completely shredded, depending how massive they are, how, I don't know, whether they are close to the jet or close to the cocoon. So, and there is also interaction. So there is some of the cloud gets ionized by the interaction. There is a cocoon of shock gas that gets created because of this interaction. So it's not only the jet passing through the medium, but it's this cocoon around it that is very important. It's a key in this type of simulation. The simulation are by far not complete. They don't consider all the coal gas, where I get in a moment, but still, they are much more realistic than what we had so far. And the other thing that I want to emphasize is that they also look at what is the reaction of the medium as a function of the power of the jet. There comes power again. So we have here two simulations. This is a 10 to the 44, just believe me, is on a lower side as a jet power. Not super low, but okay. This is as low as they got, and this is a higher power. It is quite powerful jet. So you should see both. You should look both at the way the jet goes through, how long it takes, and what kind of interaction. So this one is a powerful jet. So of course it gets more easily through. Just dump everything aside. Let me go through, and that's it. And this is what happens. This that is less powerful, of course, the medium affects also the jet. So it's not only the jet affecting the medium, it's the medium affecting the jet. You see, it's broadening, it's more, yeah, it really struggle, poor jet. So, and if you look also again at the time, this takes much longer. So if you have a really low power jet and a very dense medium, the medium can even partly destroy the jet in the first phase. But still, the energy that the jet carries, because the black hole keep on pumping relativistic electron, is dumped in the medium around. So eventually the jet can come out. As you see, well, no, you don't see because I cut away the label, but these are kiloparsec. In this, so it's a very central region of your galaxy. And this is a jet that just started. So you have a jet, you have nothing, you have the clumping medium, and then you trigger a jet. And this is why this first phase that yesterday I reiterated so much is very important, because the jet is surrounded by this medium and goes through and makes this mess. Of course, once that this channel is open, the effect of the jet must change because it has already made the channel. And so this is why the first phase is important. The other thing that this group did, very active group, very interesting work, is of course you don't know how the jet is oriented with respect to your galaxy, if the galaxy has a gas disk, whatever. So depending what is around the jet, the gas and the plasma can escape in various directions. So like in this case, the jet is not quite perpendicular to the disk, but inclined, and so try to go out the plasma in following the path of least resistance, of course, like we all do in our daily life. Okay, so the conclusion of this, because these are very important, these are simulations that have changed a bit the field of, as Alberto can confirm, have changed the field of is a jet at all relevant for negative feedback. And so, summarizing briefly this, your radio jet can indeed prevent the cooling of gas that may come in accreted in your galaxy, but can also, in certain situations, drive the outflow, and they can also, in addition to really only outflow gas that should leave the galaxy, can just make a mess. So increase the turbulence of your medium. That is another important parameter we tend to ignore. We just tend to look for outflow, but actually if you inject turbulence, you also make difficult to create more stars, because the stars, they have to, in order to form, they have to beat this turbulence. Okay, but I'll concentrate on the outflow for the moment, that we thought they would all solve our problem. Let me just also mention to you, in case you bump into an outflow in your life or in your academic life, or there are so the outflow, the gas outflow, is really gas that we think doesn't belong to any quiescent gas, and so is disturbed, and in most of the case leave your central region of the galaxy. As you will see, very seldom the outflow that we find so far, except for few extreme objects, really leave the galaxy. The gas really leave the galaxy. The outflow that we tend to find are more kind of fountains. They are, the gas is pushed out, but the escape velocity, they never reach really the escape velocity, so they probably flow back, the gas flows back. But still, if you observe gas deviating from quiescence, so if you have a disk, then it's easier, you know what is the rotation velocity, you can see when the gas deviates from that. So it's not always straightforward to really identify an outflow, but most of the case is, and you, if you have a emission line, or even absorption line, you measure in particular this wing, very often are blue shifted wing, because it's gas coming toward you, if it's an outflow, although it doesn't have to, but okay. This broad wing of your emission line, or absorption line. And then from that part that deviate from the rotation or from quiescent gas, you can measure the mass outflow rate, so you can measure the mass in the outflow from the luminosity of the line. You need to know the size. The size of where the outflow happens. That's a tricky one, because there are not always observations so detailed, I tell you, but we are very creative as astronomy to come up with some size. And the velocity that of course comes from the profile of your line. So you have a mass outflow rate. How many solar mass per year gas leaves your region. And then from this mass outflow rate, you can derive the kinetic energy of your outflow. That is an important parameter, because as I said before, you can compare this with the energetic that you have in your object. There are a number of formula. I'll just the people. There are strong discussion about which velocity to use, and there is an entire community of astronomy discussing this. But so anyway, what I wanted to say is that you can use the kinetic energy of the outflow then to compare with your bolometric luminosity of your AGN, if it is an optical AGN, or with the energy in the jet, if you think it's the jet that produce your outflow. And very important, at the end of the day, what you want to say is whether the kinetic energy in the outflow compared to the one of the bolometric energy of your object is similar to what people put in their cosmological simulation. Now, this is another source of big discussion, but let's say the original cosmological simulation were saying that about 5% of the Eddington luminosity has to go in outflow for the outflow to play a role. So the simulation that I show at the beginning, the cosmological with this burst every now and then, at least 5% of the Eddington luminosity has to be in the outflow. This is we are rediscussing this number, but it has been a reference point for the community for many years. And very seldom we get to this number, actually. But the other thing that you can do, of course, is to compare your mass outflow rate with the star formation rate, because all this we do to prevent either the black hole to grow too much or the star formation rate to keep on going. So you can compare the mass outflow rate with the star formation rate of your galaxy and see whether the mass outflow rate is comparable or anyway a big fraction of it. Although we are talking about different time scales, so that's another kind of worm that I'll spare you. So now I would like to go to some of the data that focusing on the evidence and the work, some of the work done on the radio jet and the production of outflow from radio jet. So actually, it's something that we haven't discovered yesterday. I mean, there is an entire literature, in the 90s even, showing that jet can produce outflow or can disturb the gas. And in particular, is all based on ionized gas. Because everybody was thinking, well, if the jet hit the cloud, hit the gas must be ionized. So that is where we should look for the outflow. And indeed, there are some very nice examples. There are plenty of examples in younger radio sources that are really the one where we keep on finding outflow. So this is a tiny radio source, is 100 parsec, few millisecond in radio. This is a radio image. And if you look in the optical, these are the oxygen tree lines that they have multiple components. They are up to 2,000 kilometers per second. You see here, this is the gas quiescent, and this is the width of the emission line at the location, the central location of the radio emission. So very broad. And this is a typical, we consider a typical case of outflow. And also, this is a more statistical study where the distribution of the oxygen tree, the width of the oxygen tree line for evolved radio galaxy, still the central part, and for younger radio galaxy is shown, the cumulative distribution. So you see the difference, systematic difference, young radio source is showing this. This is again ionized gas. Fine. There are also really nice example, and this object I will be my reference object for the rest of the talk. There are nice examples like this for you that are optical, mostly I think optical astronomers. This is a tiny radio source of a kiloparsec in size, still larger than the one before. And these are the H alpha, and yeah, H alpha and nitrogen 2 lines. And you see this object is this radio source is embedded in an S0 galaxy, so there is a disk in there. And you see the regularly rotating disk on the large scale here, this in this spectrum, optical spectrum. But in the region coincident with the radio, the kinematic of the gas is really a mess. So only at that location. This is something that recurrently we see. And that the location is very important, of course, to say, okay, that must be the jet doing the mess, as you will see in a moment more. Now, one thing, though, is that the ionized gas always carried a quite modest mass in the outflow. So if you look, this very spectacular case is a fraction of solar masses per year that is in the outflow. So, well, okay. Should we care about this? Is that relevant or not? So that's where we were until a few years ago. But then one thing happened that I want to stress here. So together with the simulation that came online, the more realistic that I told you, the other part that is really exciting is that actually coal gas has been found associated with the outflow. Now, this was really a surprise, because if you have outflow of 1,000 kilometers per second, or many hundred kilometers per second, you don't expect coal gas in it. And so this is some work that we have done using the H1, so atomic gas, neutral gas. So it's a 21 centimeter line in the radio. We don't have the sensitivity to see the emission, so we see an absorption. And what we see is gas at the systemic velocity. Trust me, this is about the systemic velocity of this object that was known for ages. Okay, but then we start seeing this very broad wing, blue shifted wing. This is gas in absorption, so it has to be gas in front of your continuum source. So the blue shift really tells you without any doubt that the gas is coming toward us. So this is H1 gas moving out at more than 1,000 kilometers per second and giving mass outflow rate of about 30 solar masses per year. So now then we get in a more interesting regime. And so this is already surprising in its own right. I mean, the fact that you find out H1 was already how come, but also the numbers became more interesting. But the real breakthrough came also with cold molecular gas. So cold molecular gas associated with the outflow. This is the first object where it was found. This is Markarian 231 that we're still discussing whether it is an AGN, but it doesn't matter. It's certainly a gas, an object where a lot is happening. And so this is the CO profile, so molecular gas, the integrated profile done with Iran. And if you can see, the wing of this CO, they extend for more than 500 kilometers per second each side. Actually, they reach the 1,000 here. So you have gas really flowing out at amazing velocity for molecular gas. How can it even exist in this condition? That was the question. And so this made the business, together with the simulation, made the business very interesting, because now the mass outflow rate become very interesting. In this case, that is also Starburst galaxy. They get to more than 100 solar masses per year in mass outflow rate. So that then starts to be interesting. So what the status was essentially that, first of all, we discovered that the gas outflow rate are not only of are not only of ionized gas, that all the gas gets ionized in this harsh process, but there is a component of cold gas, and actually this component could be the most massive, and is also the one more connected to star formation, because from molecular, this is an H1, this is where you form your stars. So more relevant for your feedback. And then of course, ALMA came along, and ALMA, yeah, really is the instrument that now has opened up all the possibility for doing this. And there is a really, it is a field that is expanding now, because not only can observe your molecular gas, okay, fine, but ALMA is an interferometer. We get back to the lesson one. So is not that you need to, like ELT, you need a big mirror, bigger and bigger, and larger and larger. ALMA is an interferometer. You have 60 and plus dishes, and the dishes can actually be moved in the plateau where ALMA is located at 5,000 meters. So you can have a long baseline, as you remember last one. You can have a long baseline, so you can go to very high spatial resolution. You can really see where the outflow is happening and study in detail. So that's really included, considering the sensitivity of ALMA. This has been the breakthrough, I would say. So it is at the moment my favorite telescope, even better than LOFA. So okay. So I just thought to show you a few the result on a particular object that is the same that I showed you before with the ionized gas so messy. Just to illustrate what we do in this. I had 1,000 of objects to show you, but I picked this because yeah, maybe it's more complete. So this is actually is a Cepheid-2 galaxy in the center of this, has a quite strong emission line. It's about not even a kiloparsec in size. So this is the radio emission, has a core and 2 lobes connected with some jet. It's a radio quiet object. I told you not to say radio quiet, but still, it's a radio quiet object. So it's very low luminosity radio. So a perfect object to see what is going on, what kind of damage this tiny source can do to the gas. Is an S0, is also in an S0 galaxy. This is the dust lane seen by HST. So this object was observed with ALMA, cycle 1 we started. Whoa, that was long ago. And actually only half of the antenna were online, but still, this is the detection, easy detection, a lot of molecular gas. So this is the molecular gas in the disk of the S0. And this inner part is where your radio source is. So this is the contour of your radio source, and this is saturated, but this is how the molecular gas distribute around your radio source. So already here you see something is happening in the center where the jet is. Okay, so I also thought to show you how a cube, a CO cube may look. So far I've shown you continuum image of radio. You know, you have the radio, you have the image, one frequency down. But in CO, when you observe line, like you do with the iFlu, you have a cube, and you can follow the kinematic of the gas in the cube. So this is your total intensity, so all your CO, more or less, a bit turn for convenience. The same that I showed you before. I just turn it around for convenience. Oops. And in this part, I'm showing you a cube of the CO emission going through your y-axis. So you have here a position, the x-axis, the right ascension, and then on this axis you have the velocity. You can appreciate the kinematic of the gas as you move in the cube, and then at a certain point you will see this cut cross the region with the radio source here, and there is where the mess will start. Okay, let's see if it's clear. And this here, you can see the radio source, so you can also see the region where the radio plasma is. So here you just keep on going through, whoop, whoop, and then when you get to this region where the radio is, you see how broad in velocity your the distribution of your gas is. Okay, makes sense? Yeah, yeah. I don't see any reaction, but I assume it makes sense. So this is how you can estimate what is going on. So this is actually the rotation curve of your gas, of the disk of the galaxy, just rotating. So it's a rotation curve like our galaxy, yes. And this is all deviating from that quiescent gas. So this is the part that gives you the outflow. So you can isolate it from the regularly rotating and derive all the parameters, you know, the mass outflow rate and all this stuff. So this is a summary of the movie that I showed. Again, this is the rotation curve for the disk specific of this galaxy, and all this is gas for which you need energy pumped by your AGN to disturb in that way. And you actually can derive mass outflow rate, and you see the molecular gas has a significant mass outflow rate, while the ionized gas that has also this mass is very low. You can derive the kinetic power of the outflow, and you can also see what is the bolometric luminosity of your AGN, because this is a CIFER, so is an AGN, and the jet power. So you can do plenty of energetics in this if you have this data and this kind of information. So this is what we do. And in this specific case, in principle, both the radiation and the jet can do the job, although the jet clearly reproduced the kinematic, as you will see in a moment, but only a small fraction of the gas will actually leave the galaxy. This is an outflow that reaches at most a few hundred, 700 kilometers per second at this location, and only this part may leave the galaxy. And most of it will rain back. So this is what we keep on seeing. I picked one object because it's more, I thought more interesting, but this is something that we keep on seeing, we as a community, not we as me. So that's different from the burst that I've shown you in the cosmological simulation. That such a burst we don't really see, except in some very special object like Uller or big star forming. Let me just say that for this specific object we have also compared the data with the simulation, the same simulation that I've shown you before. This is really fun. It's something that really was not possible before, so you can model, you know all about this guys, you can model your disk, you can drive a jet of a certain power, and you can see what happens to your velocity and compare to the one of the data that you observe. So we are not 100% there, but the trend is really reproduced. And so this is an indication that the jet, a tiny jet, can do at least this mass. So, what the conclusion in general, as I said, there is an entire community work on this, because this is really exciting to do, especially with ALMA. But so there is a growing number of this AGN that shows outflow of cold molecular gas. I should have put the cold here because there is also the warm component that JWST will see, but at the moment this is the most extreme cold component of molecular gas. This we are still trying to understand why there is coal gas there. The idea is that the clouds that we have seen in the simulation get partly destroyed and the gas is dissociated, photodissociation by the interaction, but then they are so dense that they can rapidly cool and reform. And so also on this there are many simulations that requires all the chemistry inside that have been done. Interestingly, so we see the coincidence, spatial coincidence between the jet and this disturbed gas, also in low power or radio quiet jet. So this is interesting. This was one of the goals of many of these. So we can use this low power radio AGN. They will do something to your galaxy. But what will they do? So far, we have seen outflow, fast outflow, only in a limited region of the galaxy, really the central region, kiloparsec. They don't go much farther. And the velocity and the gas will not completely leave your galaxy, the potential of your galaxy. So the conclusion, at least my conclusion, after seeing the result that many people are getting, is that the outflow, although very important, very interesting also from the physical point of view, because it's something that we really did not expect to find in AGN, not only radio, but in general in AGN, outflow of cold gas. They cannot be the whole story for providing the negative feedback. So we were hoping to be done and to have the recipe for solving all the problems, but clearly this is not enough. And I think the community is going in this direction. So I've summarized a bit in one cartoon. I have no time to justify this cartoon, but so the idea that we have now at the moment is that the outflow is really in the inner part of your galaxies. There is where the jet or the radiation, of course, can affect the gas. So the gas will not accrete and grow your central black hole. So that's another effect that happens. But as you go to larger galactic size, so few kiloparsec, for example, the outflow must be replaced by something else. And so the cocoon that you have seen in the simulation must already work there in a sort of maintenance mode, so prevent the cooling of the gas more than outflowing, pushing out the gas. So these two mechanisms should be not so separate as the simulation at the beginning I mentioned, so quasar mode, maintenance mode, but there is something happening and evolving, certainly as the jet goes through your galaxy. So that's and the increasing of the turbulence that all this gives. So there must be much more subtle effect, the one that should be at work for the negative feedback. That's a bit, in a way, depressing. We thought we would solve this in no time, but in a way, it's also really exciting because we get to the detail of what is going on in the galaxy. So actually, I finish. I have just 2 slides of final remarks. So my hope with this lesson was to show you that, okay, AGN have to play a role, because otherwise we really don't know what else can do in galaxy evolution, but we are not there in understanding what all the aspects that are really going on. So the outflow are common. We find in more and more objects. They are also, the idea is also that they are not very long-term kind of process. Maybe 10 to the 6, few times 10 to the 6 years, so the outflow will not go on forever. So if you don't see in every object, it's also because there is a time scale connected to it. So you can be lucky or unlucky. But of course, what I'm doing and what I've focus here are the detailed study that we do at low redshift. That in a way you may say, well, okay, but everything happens at high redshift, so in a way you can take this also as a detail of the physics, the detailed physics, but then you will have to shift to the condition of the high redshift. Pity that at high redshift this detail cannot be seen, so we are trying to get the best of both at the moment. One thing that I really like is that while trying to understand this feedback that we really have to look for, we have learned a lot about AGN in general, so that we have discovered things that we did not expect because we looked a bit out of the box. So I thought this was a nice process, at least I found as a very exciting process, like to discover this kind of thing that at the beginning really nobody could believe. They were really doubting the observation because nobody could believe that this type of outflow would exist. And so, and by now there is really a role for the radio jet, even the radio quiet sources. So this is also interesting because the community is getting more and more interested to this. That is nice. And just the future, some tip, I don't know. So the multi-wavelength is clearly something that we do all the time. So I've been focusing on radio, but actually all my work is done by looking also at whatever else is available. And it's getting easier and easier, so I really strongly recommend you to keep an eye on open for whatever else can be available for your object. It doesn't have to be an AGN. This is a general kind of suggestion. Because there are survey, database, archives, more accessible, so really you can do more. So stay broad. Don't end up in your own little wavelength, I don't know. And when possible, if you want to do statistical work, really try to select sample maybe in nice area. There are so many nice area with many ancillary data, and they are really growing as we go. So, and it saves really a lot of trouble because write proposal and get the disappointment of not getting time is very depressing. But so there is really time to save and energy to save in this. So I've been telling you about the radio AGN, the continuum emission, in which I mostly concentrate on LOFAR because this is also, well, has really opened up some new field, but is of course in the northern hemisphere. So the northern hemisphere has been so far very good because most of the work was done for the continuum with the VLA and all this, so we can do a great job. But the future is probably more in the southern hemisphere. So watch out for that. So is the Meerkat, but also the SK that will come online with part in Australia. So there is a lot of potential and also a new way to do radio astronomy. So hopefully it will be good also for you without getting all this Fourier transform. And ALMA combined, of course, in the south hemisphere, has really a lot of potential and a wonderful archive with all final product. So really easy to interact with. So something that you should, consider. And it's great because really can go to high spatial resolution. So depending on your work, can really tell you what is going on in the center. And so these are my suggestions. I hope that even if you don't care about AGN, I know that is a tiny minority in the audience, at least there is some, well, first of all, your general knowledge, you will encounter some AGN in your life, but also in general, considering opening up and taking into account the possibility that not only the AGN, but in general the radio offers to you. You know a little bit more now after this full lesson. Thank you for listening. Thanks.
Thank you very much. much, Raffaella. Very nice talk. Questions?
Hi, Raffaella. Thank you very much for this very nice talk. So it's not my area, but when you say AGN wins and also AGN outflows, are they the same thing?
That's the philosophical question that I was I was hoping to avoid. No, 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 no. Well, no, no. There is a discussion on the physical idea. So this the wind are really the something that you measure really close to the accretion disk. So it's really the radiation that comes straight away from the accretion disk. So usually they are the so-called UFO, terrible acronym UFO, but okay, ultra fast outflow that have been detected in X-ray. So it's a super high ionized gas detected is mostly absorption in X-ray, and this is really considered radiation very close to the accretion disk. Then as soon as this leaves, interact with the medium, and so the radiation interact with the medium, there is where the outflow, so really the material getting out. So there is, I don't know, there is some physics and some just different type of nomenclature. Yeah, but we have been discussing this a few weeks ago at the workshop, and the decision was that the outflow are really the ones that are carrying gas on larger scale. Does it make sense? Okay, good.
Just naive questions. So you say the outflow doesn't provoke blow away of the gas, but what happens to the gas that the plasma that is thrown into the lobes? Does that interact? Does that leave the galaxy?
So this is plasma. This is the magnetic field. So you need the magnetic field and the electrons. That goes and may also disperse because some of the plasma will also interact with clouds and deviate and can deflect and whatever. But the gas, so when I talk about outflow, in this context, is really the gas, the one that I don't want to be around to form stars. So that gas is not the radio emitting, it's the CO, it's the H1, well, it's radio emitting, but not in the continuum. So that's my outflow.
Mm-hmm.
Although I understand that also jet is an outflow, and indeed, but they say that's the cause, and then there is the gas that I want to kick it out.
Okay.
Yeah.
Just
Yeah.
and you didn't say much about the inflows. The black hole have to.
Well, because
somehow-
you should
is
have
it a
given me
geometric
5
issue?
lecture then. I mean, there is so much that this audience can take.
But that happens as well, right?
Well, is much more difficult to identify the inflow. So it's much more difficult to disentangle from whatever mess is around. So to pin down gas that is flowing, that's I don't know. People are looking into that because of course this is what you want to see if the idea of accreting, high, low. But that's much more complicated to, the velocity are less extreme, at least the one that where one can still follow the cloud, less extreme. I don't know. So, but there are cases, yeah.
Final. You mentioned that you could compare the outflow rate with the star formation rate, for instance. But are these two things disconnected or?
Well,
Or you just measuring a big thing bigger than the small things?
some people are very keen. I didn't get in too much this, but some people are very keen of this mass loading factor, whatever the ratio. Other people are very critical because they are completely different time scale. So the outflow can be, as I say, 10 to the 6 goes. The star formation rate, the star forming takes longer. So what does and sometimes they are not co-located. That's the other tricky bit. there is one object where maybe you see some anti-coincidence, but it's so comparing gives you an idea whether the outflow does what it's supposed to do, really get rid of a lot of gas, but then to really connect the cause effect is
Thank you.
Thank you. Actually, I have small two questions. First of all, I would like to ask that you mentioned yesterday about selection process. What are best conditions for best candidates for you? And second one is we talk about cold molecular gas. Actually, I couldn't understand. Can you repeat a little bit? Thank you.
so the selection, well, yeah, the selection. So in the simulation, I've tried to show you that there are different parameters. So you want the jet. The jet is very effective when it starts. So you want young radio source and see what it does. But then the effect can be different if it is low power, high power, if it's inclined. So we are trying to do, in general, as actually almost as a community, is to fill this parameter space because nobody can have so much time without us. So we are trying to build. So this work, unlike the one with lo-fi, in which you have millions of sources, this work is still based on 10, 20, 30 objects selected by various groups. We are still at we are not at the really statistical part. And that's, that's the time that we get with ALMA. So, but we are getting there in defining some of the general trend. So that's for the difference with yesterday. For the molecular gas, this is a molecular gas. I mean, the cold gas that you trace at the millimeter wavelength with, in this case, the CO, and as a tracer of the H2 molecule.
Actually, why are you thinking? Why exactly this is cold?
Well, it's cold because it's really the colder phase is when it's 50 Kelvin is already a bit hot, is even lower. So it's really the colder gas, the colder condition of the gas. While the ionizer is 10,000 Kelvin, the hot of the X-ray is 10 to the 6, 7, whatever. This is really the colder phase that you can have in your distribution of gas. So that gas gets, the physical condition of that gas gets upset or changed as soon as you have some interaction. In fact, if you look at some of the line transition of the CO, you see difference in the region around the jet and in the region outside the jet. Because around the jet has been already affected a bit by this interaction. So is the colder phase, that means also surprising because you would expect the molecule to get destroyed straight away as soon as something, radiation or a jet pass. While instead you see them moving out with many hundred kilometers per second. So this is why it's surprising. The other positive thing is that with ALMA you can go to 0.1 a second, 0.01 a second resolution, so you can really follow the gas all along your radio source. That's something that not even with the optical you can do, I mean, big telescope.
Thank you.
More questions? Okay, because I have one. You mentioned at the end that there is a missing piece. I mean, not up to now, the outflows are not the whole answer to the negative feedback. In your opinion, what are the candidates for the missing pieces?
Well, as I try to, so that's my view. That's really my view. I saw. Don't blame anybody, but I think that we don't see any, or maybe a couple of outflow that really um, cover the entire galaxy, 10, 20 kiloparsec, I don't know. The one that you will see in the cosmological simulation, the burst, we don't see, except maybe in some Euler, in the face of a strong starburst. So what is happening? So in my view of the possibility offered by the radio jet, there is something that could be the outflow in the very center of your source. These are my jet, and this is the region where the outflow, the kiloparsec scale. But then as soon as the jet goes out, it's not the direct interaction, but it's the cocoon around the jet that heat the gas and prevent the cooling. So it's not outflow anymore, but it's more like in the cluster, you see. So that the gas essentially it doesn't get the chance to cool down and to form the stars. This is a possibility based on a couple of objects where we see the CO surrounding this cocoon that I didn't get into.
But that scenario would apply to the radio loud sources. I mean,
Well,
those
not necessarily. Also the radio
the
wire.
radio wire also.
Yeah, the source with some radio. That's true. Could be connected with the radio. Otherwise, I don't know. Mm.
So still is we have a missing piece probably.
Yeah. We still have a missing piece, so we can keep on working for a few more years. Good.
Good.
We are busy
Yeah.
for a few more years. Yeah.
More questions?
Ah, okay. Well, somebody was very interested.
It just came to my mind that you're thinking of the interplay between the jet, for instance, and interstellar medium, but feedback is also blamed to be the source of energy in large-scale structure of the universe, right? Do they use it as just an ad hoc source of energy, or is there an understanding of how the process of energy transfer is made? Do you know?
You mean large scale structure
Yeah.
cluster?
No, large-scale structure of the universe, like
Oh,
the
yeah,
dark
yeah.
matter.
Well, there are more statistical kind of attempt to transfer more based on the fraction of radio source, the plot that I showed you yesterday, fraction of radio source that are, no, the fraction of galaxies that are radio sources, and of which mass, which stellar mass they have, and which fraction is radio detected. Those statistical work can be, with some assumption, transferred to energetic. So the energetic that the radio would bring to the entire. So yeah, there are larger scale. I really focus on the single object, but there are this kind of study. Yeah.
Okay, thank you, Raffaella. So let's
Thank you.
thank Raffaella again.